In this video, we're going to talk about the mean value theorem. So the mean value theorem literally says if f is continuous on this closed interval and differentiable on the open interval, then there exists some number c within AB, so it's in between A and B, such that the derivative of f at c equals the average rate of change on the interval between A and B. So let's think about this generically, kind of real worldy, so that we can really understand it. So let's pretend we go on a road trip and we drive 150 miles over the course of 3 hours. So our average speed would be 150 miles over 3 hours, which would be 50 miles per hour, right? That's your average speed during this 3 hour drive. The mean value theorem says, okay, at some point between those 3 hours, like let's say it was from 12 to 3 p.m., right? At some point between 12 and 3, you were going exactly 50 miles per hour. At some point, even if you were mostly going 49 and then you were mostly going 51, like half and half, you had to go through 50 miles per hour in order to get that as your average. It sort of makes sense, right, when we think about it that way. So that's what's going on, but we're going to see this graphically. So let's look at problem number 4 first. So we've got this f of x, big, ugly, cubic, great. It says there's some value x equals c, so x equals c, this got kind of cut off funny, between 3 and 7, at which the tangent of the graph is parallel to the secant. Tangent hits 1 point. Secant is connecting 2 points. That's a big difference here, okay? It wants us to draw the secant and the tangent line and then kind of approximate c. So we've got this point at 3 something and the point at 7 something. So the secant line is going to connect these 2 points, 3 something and 7 something. This is my secant. The tangent should happen somewhere between 3 and 7, where you're going to be parallel to the secant. So I think maybe right about here, if I draw the tangent line, it would be roughly parallel to that red line that I just drew. And so if I had to guess, this is at about, let's see, 3, 4, 5, 6, 5.5 maybe? So maybe C is about 5.5. So I'm just sketching this. It looks kind of parallel, that tangent line that goes at that little hump there. All right, let's try number 5. So it said function f in problem 4, so same graph here, has 2 values of x equals c between 1 and 7. So now we're looking at points 1 something and 7 something. 2 values where the tangent lines are parallel to the corresponding secant. So again, we need that secant line. Draw the tangent. I'm also going to sketch the secant. I think that'll be helpful. So I'm going to connect these 2 dots with the straightest line I can possibly draw. And then there should be 2 spots, 2 tangents, where you'd have that parallel to the secant. So again, I feel like it's kind of up here. Ish. There's going to be 1, and then, I don't know, somewhere down here maybe. That seems pretty good. So I think C is going to be maybe like 5.7, I don't know. And then the other one down here, like 2.3-ish. Those are going to be my 2 values. And again, these are approximations, but it should clearly be beyond 2, because at 2, we've got that sort of minimum, right? At a minimum, the derivative would be 0, and that means the slope would be 0 of your line, a horizontal line. That's not what's happening. So that's why I know it's got to be just past that, and it has to be just before 6, because at 6, again, we have that maximum. So somewhere like 5.7-ish, 2.3-ish, that's going to be good enough. All right, I want you to try 6 and 7, and then check back in. So pause the video and then check if you got my answers. All right, so in number 6 here, it tells us about the secant line between 1 and 5, But it also tells us this important information that we're not differentiable at x equals 4. So since 4 is between 1 and 5, that means that the mean value theorem does not work here. We cannot actually say that there is definitively a spot where x equals c between 1 and 5 where the slope of that tangent would equal the slope of the corresponding secant. So even though it's continuous on the interval 1 to 5, it is not differentiable. So our answer here would be no, because it's not differentiable on that interval. All right, let's look at number 7. So in number 7 here, we have the same function. It's continuous on the closed interval 1 to 4, and it's differentiable on the open interval 1 to 4. Because remember, the differentiable part is allowed to be at an endpoint because we only have the open interval for the differentiable piece. So, do we have some spot between 1 and 4 where we'll have a parallel tangent? And the answer is going to be yeah. Somewhere in between here, maybe roundabouts there, we would have that parallel tangent line, and it's going to be parallel to the secant, which is my red line there. So maybe C is like, I don't know, almost 3, maybe like 2.8-ish. All right, let's see some more practice. So number 8, we're given this function, and we want to find all values of C in the open interval such that the derivative at C is equal to, this is that average rate of change. So we've got the instantaneous rate of change here equals the average rate of change. And that's what tells us this is a mean value theorem problem. So let's actually prove that we can find some value here. So I'm going to kind of make 2 columns. We got the instantaneous rate of change. So that's going to be the derivative. So let's do the derivative. That's going to give us 6x minus 6. And then let's do our average rate of change. So I'm going to do that kind of off to the side. So f of 2, we're going to plug in 2. We get 3 times 4 is 12 minus 12 plus 2, that's just 2. And then f of negative 1. We're going to get 3 plus 6 plus 2 is 11. Okay, so the average rate of change is going to be 2 minus 11 over 2 minus negative 1. And now something that I actually want to edit over here is that in my instantaneous rate of change, this should actually be at C. Why can't I erase you? Okay, there we go. So that should be 6c minus 6 because it's actually at this one spot, so it's not just going to be x. Because we're actually trying to solve for c, right? So we need these things to be equal. And I'm just going to go ahead and edit this and say 2 minus negative 1. That is just 3 because it's really 2 plus 1. So let's solve. So 2 minus 11 is going to be negative 9. Divided by 3 is negative 3. So 6c minus 6 is going to be equal to negative 3. We can add that 6 and we'll get positive 3. Divide by 6 and we get c equals 1/2. Is c equal 1/2 in this interval between negative 1 and 2? Yes, it is. So that means we have found our answer. All right, I want you to use that same principle to try problem number 9 and then come back and check. Also, we're not going to do number 10. It's the worst. It's way beyond what we need to be doing in this class. So just try number 9 right now. All right, so first thing I'm going to do is write out that I need the instantaneous rate of change and that average rate of change. So let's do the derivative here. So the derivative of 5 is going to be 0. When I go to do the derivative of this piece here, we're going to get positive 4x to the negative 2. But again, I keep doing this. Let's make that a c because we're doing it at this one specific spot. For the average, I need my 2 y values. So I need to find f of 4 and f of 1. And let me change colors here. So I'm going to plug in 4 into x. 5 minus 1 equals 4. Great. And I'm going to plug in 1 into x. 5 minus 4, that's 1. Okay, so our average rate of change is going to be 4 minus 1 over 4 minus 1. That's crazy. Okay, so 4c to the negative 2 equals 4 minus 1 over 4 minus 1. That's going to be 3 over 3, so that equals 1. And really, 4c to the negative 2 is 4 over c squared. So when we go to solve this, I'm going to multiply both sides by c squared, and then we're going to take the square root. Remember, when you are solving and you take the square root of both sides, you're going to get a plus or minus. So c equals plus or minus 2, but are both of those in our interval 1, 4? So in this case, only the positive one is going to be our answer. So even though we do the plus minus, and it could have been, in some cases, if the interval was bigger, that both would be the answer, because we're only looking between 1 and 4, only the positive 2 is going to stick. All right, so for these next two problems, we're actually going to need to think about all of the theorems that we've learned so far from your gold sheet to answer these two AP questions. So the function f is continuous, number 11, for negative 2 to 1 and differentiable for negative 2 to 1. And notice how we've got that closed and then open. That's going to be handy. If f of negative 2 equals negative 5 and f of 1 equals 4, which of the following could be false? Ooh, okay, so false is really big. Now, I see that we're given 2 points here. So let's go draw those 2 points. Just to sketch it out, see what we're dealing with. So f of negative 2 is negative 5. Somewhere down here, negative 2, negative 5. And then f of 1 is 4. So we've got this point up here. Okay, so let's see which of these could be false. So A, there exists C where negative 2 is less than x is less than 1, such that f of c equals 0. So that's telling us some x value between negative 2 and 1, which are the x values given, such that f of c equals 0. So yeah, at some point it's going to have to cross through the y-axis. That's going to be our intermediate value theorem. So that was something we learned in Unit 1. So that one's actually true, which means not our answer, because we're looking for false. Okay, there exists c where negative 2 is less than x is less than 1, such that the derivative is 0. I don't know that that's necessarily true, because what if we just have a line here, there's no derivative of 0 anywhere between those. So I don't know about that. That seems like that might be our answer, but let's go check the rest of them. And this is kind of talking about Rolle's theorem, right? It's trying to give us a Rolle's theorem, but Rolle's theorem would have to be where these two y values were the same in order for Rolle's theorem to be true. So let's keep checking. All right, C, there exists a C where negative 2 is less than x is less than 1, such that f of c equals 3. So does it have to cross through y equals 3 at some point? Yeah, it totally does. Again, that's going to be our intermediate value theorem, so that one's true. Option D, do we know that the derivative must be 3 somewhere between negative 2 and 1? This one feels more like a mean value theorem, but we're going to have to check this one because that one actually has some work involved. So let's see the average rate of change, right? So if we have our two y values, 4 minus negative 5 and 1 minus negative 2, that's going to give us 9 over 3. That is 3. Okay, so that means that that one's true. That's that mean value theorem. That one's out. That one was kind of tricky. But because the derivative wasn't 0, that's what kind of told me, let's check the mean value theorem here. All right, E, there exists some C on this interval such that f of x is greater than f of x, greater than or equal to, for all x on the closed interval negative 2 to 1. So that's saying, is there some absolute maximum? And the answer is yes. So this is that extreme value theorem, where you have some maximum that is always going to be bigger than everything else. And so that's always going to be true. If you have a closed interval, you're going to have an absolute max and an absolute min. So that one's true, which means that my initial guess of B is the only false statement here. All right, I want you to read through number 12, pause the video, give it a shot, and then check back in. All right, so let's check if you got this one right. So this one is telling us we are continuous on an interval and the endpoints are equal. That's making me think this is going to be a Rolle's theorem problem. It says if there is no c where c is between -2 and 2, for which, yep, derivative equals 0. So that's going to be the Rolle's theorem. Okay, so let's see. Which of the following must be true? All right. A, for -2 is less than k is less than 2, f prime of k must be greater than 0. We don't necessarily know that that is true. Okay. Fk is less than 0. The derivative is less than 0. That has nothing to do with Rolle's theorem. Okay, now it's telling us, the derivative exists somewhere. That's not really how we talk about derivatives. I don't know about that one. This is kind of questionable. Let's see what else we got. Option D, f prime of k exists, but it's not continuous. Well, that's not how that works. You can't be differentiable if you're not continuous. All right, E, for some k, f prime of k does not exist. Ooh, okay. So we got to check, does it exist or does it not exist? Okay, so this is my sick brain trying to wrap my head around this. Which must be true? Rolle's theorem says you have to be continuous and differentiable. So what must be true that it does not have? Okay, it's this one, that it does not have a derivative somewhere between -2 and 2, because if it was differentiable everywhere, then we would have the derivative equal to 0 at some point. So our answer is E. This is our final answer.